Okay, let's look at our last example for this lecture. So here you can see with example 3, we're just defining y to be this 8 over the square root of x minus 2. And so first of all, we want to find the derivative, and you notice I'm using a new notation here, dy dx. And secondly, we're going to give the equation of the tangent line to the curve at this point 6 comma 4. And if you look at this for just a minute, I think you can convince yourself that the point 6 comma 4 really is on this curve. All right, so we're going to go back to the original definition. And so remember the original definition, we've got, oops, I don't want that. Remember that the original definition is the one where we have f of x plus h minus f of x over h, and we're taking the limit of that. All right, so just a reminder there. So f of x plus h, well, that's what you see here. 8 over the square root, x plus h minus 2, and then minus f of x all over h. And so with kind of complicated expressions like this, one of the first things that I recommend you do is take this, everything divided by h, and move that to the front as a multiplier 1 over h. And so that's the first thing that I'm going to do. You see here. So I brought out the 1 over h, and now we could just focus on what was in that numerator. And so that's this 8 over the square root of x plus h minus 2 minus the 8 over square root of x minus 2. And then you can see in gray here that I'm going to do a little bit of work term by term because I want to get a common denominator here. So we're going to do that. And so that, let's move on now then to this next part here. We have the limit again. We still have the 1 over h. And then I'm just going to combine these two over that common denominator. Okay, so that's all. For the next part, I'm just going to take this 8 that's common in the numerator, and we're going to move it over here with this part in the front. So I believe that's what I did next. Yes. So that's how I got the 8 over h. So we've got the 8 over h, and then what's left is the square root of x minus 2 part minus the square root of x plus h minus 2 part, still over that common denominator. And then at this point, hopefully you're beginning to recognize this pattern. If you have something minus something or something plus something, a lot of times it's very helpful, particularly in this case where we have the square root's involved. Try to see if you can come up with a difference of two squares some kind of way. And so that's what we're going to do. We're going to think of this square root of x plus 2 as big A, and the square root of x plus h minus 2 as big B. So what we want is big A minus big B times big A plus big B. And so that's why I chose to multiply by 1, essentially, right? Because this just 1, because it's something divided by itself, but it's what we need to get that difference of two squares in the numerator, right? Because that's going to give us big A minus big B times big A plus big B, right? So those will be multiplied times each other. Well, if you remember your difference of two squares formula, big A minus big B times big A plus big B, well, that's big A squared minus big B squared. And so that's what we're going to see in the next step. So still hanging on to the 8 over h times, then we've got the big A squared minus the big B squared. And so you can see, hopefully at this point, that that's going to get rid of those square roots, in the numerator at least. And the denominator, I'm just making sure to collect up everything that we have. So we have this part, and then this part. Okay, so just collecting up everything in the numerator. All right, so let's do the next step. So the square root, or if you have the square root of something and you square it, then you just get that something, right? I think I always use this example. If you have the square root of smiley face times the square root of smiley face, well, you better get smiley face, right? So that's what we mean by square root. So big A squared is just x minus 2. Big B squared is just x plus h minus 2. And then we still have that big denominator. And so then notice that once we were able to get rid of those roots in the numerator, then we could cancel out the x's. And then the negative 2 minus negative 2, that's gone. So essentially we have in the numerator, we have the h left, and we have negative, don't forget the negative, and the h there. And so you'll see at the next step, that's what I have. I have the 8 times the negative h over, and here we still have the h there and the big denominator. Oh, so now the h's will cancel, and so we'll have negative 1 left in the numerator, because remember negative h, that's just negative 1 times h. So the h cancels. And then once you cancel out the h's, once this is canceled out, then we can just plug in, right? So we're taking the limit as h goes to 0. So now everywhere we have an h, we're just going to put 0. So that gives us this step. And then from here, it's just algebra. And so you get negative 8 over, well, this is the square root of x minus 2 times the square root of x minus 2. Well, that's just x minus 2. And then here in this parentheses here, we have the square root of x minus 2 plus the square root of x minus 2. Well, that's just 2 of them there. And so that gives us negative 4, right? Because the negative 4 is this negative 8 divided by that 2 part. That's where the negative 4 comes from, right here. And then the x minus 2 to the 3 halves. Well, you may remember from algebra, or maybe not, but when you write a rational exponent, that is power divided by root. And so this is what we had. We had x minus 2 to the first power. Well, that's 2 over 2, right? That's 1. And then I'm forgetting the 2 for now. And then I also have the square root of x minus 2. Well, the square root of x minus 2, that's just x minus 2 to the 1/2. And so we have like bases, and so we just add the exponents. And so that's how we got the x minus 2 to the 3 halves. Okay, so again, if y, our original function is this, y equals 8 over square root of x minus 2, then the derivative is dy dx, and we've just determined that dy dx is equal to that, negative 4 over x minus 2 to the 3 halves power. And so just as a note, we just sort of exercising our new notation, we could have written the derivative with respect to x of our original, this is our original y equals this, is equal to this. All right, so that takes care of the first part where we were trying to find the derivative. Now we're going to use the derivative to find the equation of the tangent line to that original curve, Remember, the original curve is y equals 8 over square root x minus 2. So this is the curve that we're looking at, and the point 6, 4 is on that curve, and at that point there's a tangent line, and we're trying to figure out the equation of that line. Okay, and so remember, to get the equation, if we know a point and we know the slope of that line, then we can write its equation. And to get the slope, well, that's where the derivative helps us. So we're going to take the derivative and plug in this x value of 6. And so it's just -4 divided by, and then you just plug in the 6. You can see we plugged in the 6 right there. And simplify, and so we get that the slope is -1/2. And so our equation is y minus y1. Remember, our x1, y1 is here. That's the 6, 4. So y minus y1 is equal to m. There's our m. Times x minus x1 there. And then lastly, if we want to look at a picture, now on the test, if you work this problem, you know, when you get to this equation, and you've also given me the derivative, so this part and this part, that answers the question. But just for your understanding and your edification, let's look at the picture and kind of see what's going on. So like I said, this part is not required. But one thing to note is I did a little algebra with this tangent line equation, and that gives us what you see here in red. Okay, so that's just the tangent line in the slope-intercept form. You may remember that. All right, so again, the original curve is y equals 8 over square root of x minus 2. That's what you see plotted here in sort of this gray, dark gray color, I guess. And you can see the 0.6, 4. And then this line in red, that is our tangent line. And, well, let's see. If you remember from the slope-intercept form of a line, the y-intercept is 0, 7. And if you look at this this line, well, it looks like it's going to hit that point 0, 7. So that makes sense. And let's see. Well, let's see what else can we, because we've got the equation of the tangent line. We've plotted the original curve. Let's just review some things from, you know, that section on limits. Well, one thing that you may notice from this curve, it looks like the x-axis is an asymptote, and it is. But so why? Why is that x-axis, or, you know, the equation of the x-axis is y equals 0. Why is that an asymptote? Well, it's because of this limit here. If we look at the limit as x approaches infinity, that's equal to 0. And that's because we've got a fixed numerator, but then the denominator is getting big, big, big. And remember, fixed, or you can think of it as small, over really big is really small, and that goes to 0. And similarly, we've got another asymptote, which is x equal to, I don't know why I put y there, that's x equal to, that's this line here, and that is an asymptote. And why is that an asymptote? Because of this limit. If you take the limit as x approaches 2, right there's 2, and if we take the limit as x approaches 2 from the right, then we're going to get infinity. Okay, so why is that? Well, if we plug in, notice the form here of this limit here. The form is 8 over 0. And as we approach, as x approaches 2 from the right, that denominator gets smaller and smaller, but it's positive, and so that's why it is infinity. Because if you take a fixed number over something really, 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 really small, then you're going to get a big, big, big number, right? It's going to keep getting bigger. So as you divide by smaller and smaller numbers in magnitude, like you divide by 0.1, 0.001, and so forth, then what you're going to get is something bigger and bigger. And so that's why that limit is positive infinity. And so that's why we know that we have those two asymptote lines.